All right, so this is Pre-Calculus Lesson 6.3, Day 1, and we're going to be looking at vectors today. And a vector is represented by array, and a vector has both magnitude and direction to it. And so the magnitude is going to really be the length of that ray. And we talk about it having an initial point P, and a terminal point Q. And then this is the notation for it. We just have P and then Q, and then we put this little arrow on it. And when it's drawn like that, it is always that P is your starting point and Q is your terminal point. And the magnitude, which is the length of the vector, is denoted with this absolute value. It's kind of a double absolute value. So when you see this on the outsides of that notation for the vector, that means they want you to find the length of it. And you're going to be using the distance formula to find that. And we'll model that in some of these examples. Two directed line segments that have the same magnitude and direction are equivalent. So all of these are considered equivalent because they are parallel and they're going in the same direction and they have the same length. So wherever you place this with the same magnitude, same direction, they are equivalent vectors. And so the set of all directed line segments that are equivalent is a vector V in the plane. We use these lowercase bold letters to indicate a vector. So notice that lowercase v can also replace that vector PQ. They're the same. They're just different notations for a vector. All right, showing that two vectors are equivalent. To show that they're equivalent, you have to show that both magnitude, so that's going to be using the distance formula, both magnitude, and for direction, we are going to use slope, and we have to show that those are both the same to show that vectors are equal. So we have to have the same length, but we have to say that they're going in the same direction as well. And so that's why we also have to show the slope. So we have this vector u. So there's one of those lower bold case letters used for a vector. Let it be represented by the directed line segment from P is 1, 1. So we're going to come here to the right 1, 1. That's P. And Q is to the left 2 and up 3. So here's P, here's Q, and you're going from P to Q. And so that's that directed line segment. And that is also given, come back. That bold lowercase u. And then it says let B be represented by the directed line segment from negative 3, 0 to negative 6, 2. So this is R, this is S, and again, we have another directed line segment. They look like they're about the same length and in the same direction. But you have to show it mathematically. You have to show it mathematically. And so we have this, P is at 1, 1, and Q is at negative 2, 3. We're going to use the distance formula to show the magnitude of vector PQ. And get used to that notation. And the distance formula, it's your change in x squared plus your change in y squared, and then the square root of their sum. That is your distance formula. And so it is your negative 2 minus 1 squared. It is your change in x minus 2 minus 1 quantity squared. And then plus your change in y quantity squared. Again, change in y. And continue to evaluate that. You get a negative 3 squared, which is 9. You get 2 squared is 4. And that magnitude is the square root of 13. Well, you need to find the length of RS. And R is at negative 3, 0. And S is at negative 6, 2. And notation, magnitude of vector RS. And again, we are going to find that change in X. Oops. Plus the change in Y. And you end up with a negative 3 squared, which is 9, and 2 squared is 4. And once again, you've got the magnitude of the second one is root 13. So they have the same length, but that's not enough. You have to show that they have the same direction. And for that you are going to do slope. And the slope formula is your change in y over your change in x. So vector PQ is also known as u, so I'm just going to say the slope of vector u. And I'm going to use these same 2 points. I'm going to use the same 2 points. Change in y, 3 minus 1, over change in x, a minus 2 minus 1. And so you get 2 over a negative 3, and you have a negative 2/3. And then we need to show the slope of vector v. And so we're coming down to the 2 points R and S. And slope is change in y, so 2 minus 0, over change in x, a minus 6 minus a negative 3, is 2 over negative 3, or overall a negative 2/3. And so therefore they are equivalent. They have the same magnitude and direction. They are equivalent. So it takes both showing that their length's the same, but that they're going in the same direction, which is your slope. All right, so, well, we have a component form of vectors that just makes some of these calculations a little bit easier. So I'm just going to use this QP up here just kind of quickly. From P, I can create this right triangle. And from P, I'm going to the left 3 units. And then I'm going up 2 units. And so component form of PQ is minus 3, positive 2. A minus 3, positive 2. That is the component form. And that just already, the horizontal change right here was negative 3. The vertical change was 2. And so you're getting that length of the sides of that right triangle, and that is going to make calculations for distance easier because you already have the change in x, you have the change in y, and you can do some calculations a little easier. So component form, it looks like this. And we're going to see how to calculate that on the next page. By the way, if you start at 0, 0 with your vector then it's going to be in standard position. So if you draw a vector where you start with the initial point at 0, 0, it's going to be said it's in standard position. Let's move on to the next page. So how do I find the component form of a vector? With initial point p sub 1, p sub 2, and terminal point q sub 1, q sub 2. Order of how you subtract these is important. Order of how you subtract these. P is your initial, Q is your ending. You must start with the Q, and it's Q sub 1 minus P sub 1. So Q sub 1 minus, it's terminal minus initial to get the correct signage on this. And that's your horizontal component. And that will get the sign on the horizontal component correct. And then the vertical component, how much it rises, is Q sub 2 minus P sub 2. And then this little caret kind of thing, kind of like a less than and greater than symbol, those are just the symbols that we use for component form. And so a vector can be written in component form. You can use a lowercase bold letter for it, and this is also a way to indicate a vector. But the nice thing about the component form, which I was trying to show you before, is that distance between Q sub 1 and P sub 1 is that horizontal distance. So when it's in component form, to find the magnitude, you can just take V sub 1 and square it. You can take V sub 2, square it, add those together, take the square root, and you get the magnitude. So a very quick example is, say that you have vector V is negative 2, 1. The magnitude of vector V is you just square the 2, square the 1, and take the square root of that sum. So when it's in component form, some of the work's already been done for you in a sense. It's kind of nice. So that's how you can use the component form to find magnitude. And if the magnitude happens to come out to be 1, it's called a unit vector. It has a length of 1. And if the magnitude is 0, it is the 0 vector. It's like a point. There is no magnitude. It has 0 force to it. It has 0 force. And two vectors are equal only. You know, an example of equal vectors is if this is negative 3, 2, then the only way they're equal is if their components are identical. That's the only way that they are equal. Okay, so example 2, find the component form and magnitude of the vector. So you need to know your terminology, right? Component form we've just been talking about. And then the magnitude. But it has an initial point, negative 3, 2, and terminal here. They're going to call this vector V. So to get vector V, you must start with the terminal and subtract the initial. So it's going to be 8 minus the negative 3. That will be your, what we call horizontal component. And then for the vertical component, you need to take the change in y, but terminal minus initial. And so the component form is 11, 1. Component form is 11, 1. And then the nice thing about component form, which I tried to demonstrate just a little earlier, is to find the magnitude. 11 is the horizontal change already, and 1 is the vertical change, so you just square those, add them up, and take the square root. And note the notation for magnitude. And that's the magnitude. So it said find component form, that is this right here, and then the magnitude. Are you, have that in that type of bracket? Are you talking about this? That indicates its component form. That's component form. Yep. All right, so we also have what we call scalar multiples of vectors, and it's just making the length shorter so the magnitude, the force is less or larger. So right here, we have vector v. If I take half of vector v, it's a vector that is half as long, meaning its magnitude, which is often force, is half of what it was. If I double the vector, the length actually doubles, meaning the force, if that's what it's being applied to, is doubled. When you negate a vector, it actually goes in the opposite direction. It has the same magnitude, but it goes in the opposite direction. It goes in the opposite direction. So a negative 3/2 times a vector, it's going to go the opposite direction and be 1.5, a half time longer than what the original was. So that's what happens when we multiply by a scalar. Let's move to that next page. Okay, so we can add vectors, and when they're in component form, it's very easy to add them because all you do is take these horizontal components and add them, and that's your new horizontal component. And then you take your vertical components, you add those, and that gets you your new vertical component. That's all there is to adding the two vectors. We're going to look at this geometrically in a little bit. When you find a scalar multiple, such as when we were looking on the last page, times 1/2, times 2, times negative 1.5, all you need to do is take what you want to multiply and take each component times it, and that will adjust the vector accordingly. That is a scalar multiple. The negative of a vector is basically a scalar of -1, and you change the signs on both of the components. And I keep on saying, the first is the horizontal component, and the second is the vertical component. When I went back and I showed vector p, I think it was pq, and we talked about this being -3 and this being 2, this was your horizontal component, and this was your vertical component. So you negate both your vertical and horizontal and vertical components, and you have the negative of it. So we talked about vector addition up here. So what is subtraction? Well, it is really you add the negative of that second vector. So you really think about multiplying the second vector by -1 as a scalar, and then you add those. You do end up just subtracting the components, but we think of it as adding the opposite of it. All right, and there's quite a few properties. I'm not going to go through them too much. It's just this says you can add them in either order. They're the same. If you add the 0 vector, you end up with the same vector. If you have two different scalars, applying them in two different ways, it doesn't matter if you apply one and then the other, or multiply the scalars and apply them once. If you have a scalar times the sum, you can distribute the scalar to each and then add them. This sometimes is helpful, that if you have a scalar times a vector, you can actually take the scalar to the outside, find this magnitude, and then multiply by the absolute value of that scalar. I'm not going to spend, that's all the more I'm going to really spend time on that, but these are properties of vectors. All right. Find the sum and difference and sketch the resultant vector. So, addition. We have vector W, vector V. When we add these, we add their horizontal components and we add their vertical components. So we're adding their horizontal components, and then we are adding their vertical components. And that will give you the sum of those two vectors. All right, so what does this look like geometrically? Well, W is a vector negative 2, 5. I can start anywhere on the coordinate system here that I want to, and as long as I go left 2 and up 5, that's going to be a vector W. They're equivalent. They have the same horizontal component, same vertical. And so, but we typically, what I'm going to add, I'm going to start at the origin. I'm going to put it in standard position. So for a vector W, and I'm going to write it here because I want to zoom in a little bit because it's so small. So for vector W, I'm going to think of going to the left 2 and up 1, 2, 3, 4, 5. That's that horizontal of negative 2 and vertical of 5. And so I'm going to end right here. And so it goes in this direction. And that is vector W. And then when I am going to add V, and vector V is 3, 4. We are going to just go right from where we ended, and we are going to go to the right 1, 2, 3, and up 1, 2, 3, 4. And we're going to end up about there. So to the right 1, 2, 3, and up 1, 2, 3, 4 puts me about right here. And that is vector V. The sum of those is called the resultant vector, the result of adding those two vectors, the resultant vector. And the resultant vector is you start from the very initial and where the last terminal point was. That is your resultant vector. And it should correspond with the fact that the resultant was to the right 1 and up 9. If from 0, 0, if I go the right 1 up 9, I end up at the same spot as I did after adding them. That's the resultant vector. All right, so for the subtraction, I'm going to think of it as a negative 2, 5 plus the opposite of the second vector, which we negate both of the signs. So I'm thinking of it as W plus a negative 1 times vector V. And then when we add those, we add the horizontal components and we add the vertical components. And that is your component form. Again, I could start at 0, 0 and go to the left 2 and up 1, 2, 3, 4, 5. And there is my first one. But then I want to think about adding the opposite. So from there, I'm going to go to the left 3. And what was it? Left 3 and down 4. And I end up right there. And so my resultant vector is from the initial to here, And I think about the right triangle associated with it. Notice I'm going to the left 5 and I'm going up 1, which is what we got for the resultant vector. And so then the last one, I'm not going to bother drawing it. It's not necessary. We're going to have 2 times vector w. And since it's a -3, I'm going to think of it as a positive, adding a -3 times vector v. And so I get a -410 plus a -9, -12. And you get a -13, -2. So it's not too challenging. And that is the end of those notes.